Hi, this is Jason McLachlan at the University of Notre Dame. I want to start off by acknowledging some colleagues who've been important in my thinking and in contributions to this talk. Leah Appling, former undergrad at Notre Dame, and Megan Vossen, a current grad student. The Ecological Forecasting Initiative, Mike Dietz, the lead, and Jody Peters, the manager, and all the large grassroots open group that has made this conversation interesting and exciting. And then in particular, the education working group that I lead, and Alyssa Wilson in my lab, who's contributed a lot at the undergraduate forecasting training component, and the DEI working group that Diana Dalbotton leads, have both really shaped my thinking about this. And then finally, I'm lucky to be associated with the Geoscience Alliance, a group for mentoring Native American students across the country, led by Diana and Navita Bueno-Watts, and I'll show some of their results during the talk. The first point here is that this is a figure from a proposal that we have pending right now that sort of highlights the various ways that the components of scientific advance work together in a forecasting framework. And just to highlight that education and diversity and inclusion are the framework for all of those things, and that these things don't work unless we have that framework. All of the things that contribute to our priorities, here's NSF's rule of light, harnessing the data revolution, translation of basic science into applied stuff, only work within those contexts. So I'm going to be talking about work that we're doing to sort of improve training and forecasting, but especially within the context of training undergraduates and training the groups that are not well represented currently in ecology or STEM in general. All right, so why ecological forecasting isn't just forecasting about the future, it is the future. And the reason I say that is because the response to the current movement towards thinking about ecological problems as predictive forecasting problems is tremendous. This is just screenshots from a virtual conference we had in May, and deep in the pandemic, we had over 160 people stick around for 13 hours of Zoom calls just to figure out how is it that we can tie neon data into forecasting, and a big component of that is how does that help training at the graduate and undergraduate levels. Okay, so why is this trend happening? Well, there's some technical reasons why forecasting is just an advance over the typical way we've made scientific inference in the past. We know that we have a replicability crisis in science, and you skirt that issue by making forecasts into places you haven't seen or times that you are in the future. You can't cheat. You can't overfit the data if you're predicting the future. There's other technical reasons why forecasting is efficiently solves some of the major technical problems in science, and you'll hear that in other talks. On the theoretical side, by making a mechanistic forecast, or, it's a question about whether you need mechanism. Here's one of many models on the 538 COVID-19 forecast, and they each have different assumptions about how many mechanisms they use and how mechanistic they are. All those compete with each other, and we make a forecast and we test what happens. So this both unifies science by working across scales, and it provides falsifiable different hypotheses about how the system works. And finally, these days I don't think I need to mention how important forecast models are for society. There's a diverse array of communities that have interest in ecological problems, including epidemiological, as I've shown here, but it could be climate change, it could be conservation, it could be resource management. If we engage with those communities and with decision makers, as you do in a forecasting framework, then you can gain trust, and you can gain wisdom over time, and you can stop having this divide between the academic ivory tower and the people who need and use the models. By the way, this guy, who I just grabbed from an AP photo, is not technically wrong about his sign, but I think he's wrong about the interpretation of that sign. Okay, so here's a quote that I took from Nyavita Bueno-Watts' slide from AGU last year after a survey of a large group of Native American students who participated in this Geoscience Alliance program. And I think this is what I'm getting at in terms of where STEM should be going. So she's talking to these Native kids, and all of them are interested in how the environment affects their communities. Some of them are science nerds, but they weren't interested in science for its own sake. They're interested in the well-being of their communities. And so this was in a geoscience context, but obviously the same thing applies in ecology and evolutionary biology. And it's not just Native kids who think this, right? We know that, Generation Z is the most, one of the, there's a sea change in how American kids care about the environment and what they think science is for. So how can we help make those dreams come true? Forecasting is a good way to do that. This is a figure from Mike Dietz's 2018 paper in PNAS that just highlights the forecasting cycle of iterating between data and models, and the link to adaptive management, where policy can influence the model and the results of the model can influence policy. So this is a way that science can directly engage with communities and decision makers in the design, early in the experiment of design, in how you analyze it and make it real. And that also complements a trend in pedagogical research that highlights the active investigation, authentic research, and that leads to students engaging with the material, including students from groups that are not well represented in science. That is to say, you don't have to wait until you master all the basics to be able to apply these to things you care about. And so the forecasting approach bolsters high standards of pedagogical principles that are in the literature today. So where are we now? So first of all, I just want to say that if you do a Google search for glass half empty and a Google search for glass half full, you get different images of glasses that are exactly half full. So I thought that was funny. Let's start with the half empty. We've got these disciplinary boundaries. They're in academic units. They are somewhat still in agencies like NSF, and those stop us from merging information across disciplines. They stop us from having a view of science that integrates analysis and core disciplinary ideas. Usually the quantitative training that our undergrads and grads get is outdated. People use stats books that originated before personal computers, and that's common. And that may be the only training that grads or even that undergrads or even grads get in statistics. And then finally, that training is unequal and uneven across U.S. colleges. So though some schools are crossing disciplines and some schools are elite schools are increasingly able to take advantage of free software and the powerful tools that are available, it's not even. The good news here, though, and I'm going to end with the glass half full here, is that the kids get it. They know. The students who are in our classrooms know that computational linkages to real-world problems are what science is about. So we've got a good audience ready for us. How do we do it? Well, in the Ecological Forecasting Initiative, here's the webpage. We're doing a couple of things. We teach a bunch of summer courses. Some of these are not associated with EFI, but they're complementary. This is a textbook that's out, so there's tools. There's all those courses and textbooks have freely available resources online, videos, code, etc. We're collating all this stuff on the EcoForecast webpage. And then I just want to particularly mention the forecasting challenge from the Forecasting Initiative RCN that I'm involved with, which the goal is to have a challenged to predict neon data ahead of time, and that's going to be working across many institutions and hopefully will serve as a role model for how to teach this better in the future. All right, so at the undergraduate level, things are not as promising. So I guess I would say at the grad level, we have all the pieces, especially at the schools that are wealthy and white and doing this most concertedly. So we have a pattern that we can then try to grow and learn how that works in other communities. So I think we have the pieces at the grad level. At the undergrad level, I think that if we want the future of ecology to be ecological forecasting, it has to penetrate into introductory classes. So here's the first biology class that our bio majors take at Notre Dame. There's 200 students in this lab across 10 labs. Most of them are pre-med, so most of them aren't particularly interested in ecology at first. And the focus is authentic research linked to research in our lab on the development of coastal wetlands. And we did Aaliyah Appling, shown here at the right, along with Megan Bosson, a grad student, conducted a scientific survey before and after the course, and it seems like we're on the right track. It's not a forecasting course per se yet, but it has authentic research and it has scenario-based real-world applications. And you can see that in general, people's confidence increases after the course. And we found that even the kids that were pre-med and not disciplinarily interested in coastal wetlands or ecology thought that it was useful for their professional development, and they found it to be real. We found some persistent gender differences here. The guys are more confident than the women on some things. And frankly, I would say that the fact that 80% of Notre Dame men believe that they're good at forming hypotheses means that they're perhaps a little overconfident, because that's actually kind of a hard thing to do. But we found that the course that did bolster confidence and interest in these things. So what's next? Taking that kind of scenario-based work and turning it into a true forecast where the data that the students collect actually influences their forecast of wetlands, and where in fact they can examine the impact of different decisions that coastal managers or coastal communities might make in terms of rising greenhouse gases, managing wetlands, etc. We're curating all these resources online and trying to find where the gaps are so that we can fill them, and try to take things like existing software and try to make them easier for people and make interpretive videos and things like that. We've got a long way ahead of us, but there's a lot of stuff already available. We've got proposed work to develop carpentries workshops that are culturally aware of various communities that are not well represented in STEM now. Like I said, we have a ton of short courses and online material freely available. Currently, in the future, we'd like to propose active exchanges with the partner organizations that actually use these data, so that they can start by thinking about the decisions instead of starting by thinking about, sort of basic biology. If you start with the application, the basic biology becomes more relevant. And finally, the idea is on expanding the communities that use this beyond the sort of elite schools that are using it now, is to actually go and listen to the communities that we want to engage with, instead of handing them products that we've already developed, to think about what do they want to work on and how can they help us work on this. So that's what we're doing now, and we just invite you to join us. So check out ecoforecast.org. If you have a better idea, please propose it and help us get there, because it's really important. Finally, I just want to thank various funding institutions. Shout out to National Science Foundation and Notre Dame, and to the grassroots groups that are working to make this happen, the Geoscience Alliance and the Forecasting Initiative. All right, thank you very much. I appreciate your time, and I'm looking forward to the discussion session.